Hello and good day, Algebra. We are picking up where we left off last week, Greens and Timeout, with CO5, converting from scientific notation to standard form. And you shared with me last week that you have some experience with scientific notation. It's okay if you forgot. The important thing is you have the experience. We are recording, mind you, so the side conversations cannot be happening. Those of you that do remember something from scientific notation, what can you tell me about it? What can you tell me? Kylie?
Something that you do to help read a number easier if there's a lot of zeros.
Sure, if there are a lot. Okay, so it helps us read a number more easily if there are a lot of zeros. Arlene?
They use exponents.
It's used with exponents.
It just makes it easier, so then you don't have to write down such a big number.
Yeah, it makes it easier. You don't have to write down either really big numbers or really small numbers, basically really long numbers over and over and over again, which is how we're going to start today's lesson. Did you know that the Earth is 491,910 million feet from the sun?
Oh, I could walk that too. In 5 years.
If we were to write that number again, 491,910 million, and again, 491,910 million. If you were writing an essay, you might have to write 491,910 million lots and lots of times. Okay? Yes, sir.
Wouldn't it technically be billion, not million?
491,910 million is what I said. 491,910 million. At least I think I said that. We can go back and check the tape, I suppose. But yeah.
How was that proven?
I don't know. I just Googled it. I don't know. Don't ask such logical questions around here. No. I assume that they have sent satellites and tracked speed and calculated it in that sense. I don't know how. I don't know. But I was just looking for a very large number to use here. Whether it's true or not, we'll assume it is. But it doesn't matter. For scientific notation, everything that you had said, scientific notation is a way to write really long. I'll put really long because normally I put big and small, but I mean, really, I guess really long is the better way to do it. Really long numbers, a shorter way. Okay, a way to write really long numbers, a shorter way. So, those that remember scientific notation, how would you write 491,910 million using scientific notation? What are you doing? What are you looking for, Jack?
An exponent?
You do need an exponent. That is true. Ellen? Sorry? Commons can help you kind of determine what your exponent's going to be, help you with the counting. Bryn? You not only count the zeros, but you count all the way until Liesel.
You count the whole number, and then that's like the amount of exponents.
So
The amount of zeros.
Not just the amount of zeros. Arlene?
4.9191, and then you would go from the decimal point there, and then times it by 10 with the exponent.
So right now, yes. So right now, folks, hey, you don't need to announce that because we're recording, and I don't like to stop class on recording to deal with that. So stop. Right now, where's our decimal point? Aiden. At the very end. Okay? And so what Arlene is saying here is that we need to move our decimal all the way to the left until there's only one number before it. So some of you were saying just count the zeros. It's not quite just that. You've got to go all the way until there's only one number before the decimal. So what Arlene said was 4.9191. We can't drop those non-zero digits, okay? All the zeros do end up falling off. And then what's our exponent here? How many times did we move our decimal point? Christopher? 11. So 4.9191 times 10 to the 11th would be this number in scientific notation. Yes, sir? What happens when you multiply a number by 10? Like what's 9 times 10? 90. You just add a 0, right? What's 9 times 100? 900. What's another way to write 100 using an exponent? 10 squared, right? So the reason why we use powers, I mean, we could write this, a 1 with 11 zeros after it, but it's just quicker to use a power. But where that exponent comes from, every time you multiply by a 10, you move the decimal over to the right, okay? And so that's where it comes from there, okay? Is it coming back?
Yes.
No, if it's not, it's a good thing because we got more to practice, okay? If it is, then good job paying attention last year, I guess. All right, there you go. Rewrite in scientific notation. The first one, 5,670,000. Again, what we're doing here is we're thinking, where's our decimal point? It's at the end. And where do we move it to? How many times do we have to move it to get there? Okay? We got to move our decimal to the left until there's only one number before it. So it's going to be between the 5 and the 6. Okay? All the non-zero digits get written. 5 point now, because we moved it there, the 6 and the 7. The zeros drop off, but it's not just how many zeros there were, right? It's how many times we moved it. So it's not going to be times 10 to the 4th. It's going to be times 10 to the 6th, because that's how many times we moved the power. Okay? Next one, 878 trillion. Okay? Our decimal is at the end. And where are we going to be moving it to? Kylie? Between the 8 and the 7. So it's 8.78. Okay, we move it all the way. There's only one digit before it. The 8, the 7, and the 8 get written. All the zeros drop off. And what's our exponents? Catherine? 14, you said? Okay. And here's how someone said commas can be helpful. I mean, every comma is a movement of a 3. So you can kind of count 3, 6, 9, 12, and then your extra 2 to get 10 to the 14th power. Right? For really, really small decimals, because in science, you deal with really, really small measurements, right? The measurements of atoms and quarks and other sciencey words, okay? So in this case, with a really small decimal, what do we do here? Because here's our decimal. It's already, kind of shoved all the way over to the left there. Ellen? This time, we move it to the right until there's only one non-zero digit before it. So it's going to be between the 1 and the 3. Really, the whole point of this is to drop off the zeros. Get rid of the zeros. Okay? So if it's a really small decimal where it's already kind of over on the left, we're going to go to the right until we've got a non-zero digit before it. And that's going to give us 1.3. How many times did we move it? 4 times, right? 1, 2, 3, 4. So what's our exponent going to be? Why is it negative? Shh, raise your hand, please. Why is it negative? Alex? We moved it to the right, which means which direction we have to move it to get back to our original number? Left. Damien mentioned earlier, why do we use a power? How's that work? How does it make sense that this exponent being negative and going to the left is going to bring us from 1.3 back to 0.00013? Moving the decimal to the right is like multiplying by 10. Kylie? Moving it to the left is like dividing by 10. Right? So if we have something like 90 times 10 to the negative first, that's the same thing as 90 divided by 10. That's a horrible zero. I don't know what I was trying to do. Okay? But a negative power is the same thing as dividing by 10. Okay? The last one here, 0.0000004901. We see it's a decimal, really small. Where are we going to move our decimal point? Raise your hand, please. Rowan. To the right. Where are we going to stop? Between which two numbers? Between the 4 and the 9, right? It starts here. We want to move it until there's only one non-zero digit before it, which will be between the 4 and the 9. So our scientific notation is going to start 4.901. This 0 has to be included because it's between two other non-zeros. Okay? We can't just stop at 4.9 because there is a 1 after it. So we have to include the 1. We can't just put 4.91 because now it's a different decimal. Okay? If there's a 0 stuck in between other non-zeros, we've got to include that. What's our exponents? How many times did we move the decimal point to get where it's going to be? Aiden. 1, 2, 3, 4, 5, 6, 7. And there we have it. Okay? So, why is the exponent positive and why is the exponent negative? We already kind of talked about this, but just to recap, in these first two examples, why was the power positive? Ellen? The number was on the left. What do you mean by that? The number was on the left side. We had to move the decimal left to get it to where we wanted to go, meaning that, in a positive decimal, how would you describe the value of that number? Really big or really small? Really big, okay? The exponent's positive because the original number is really big, right? We have to move the decimal to the right. We have to multiply by 10 to get back to the original value. And like we said for the second two, why is the exponent negative? Well, because the original number is really small, right? We have to move the decimal to the left to get back to the original value. We have to divide by 10 to move that decimal to the left. So the exponent's kind of important. Not only to tell you how many times the decimal moves, it also tells you which direction, right? Positive power, moving to the right. Negative power, moving to the left. Okay? Questions so far? Those that said earlier it wasn't coming back to you, is it better now? Okay? I'll start calling you Crinkle. Just Crinkle. Okay? So going down a little bit, rewriting in expanded form. 7.613, you look at that and you tell me two things. Which direction is the decimal point going? Left or right? To the right. How many times? 4. If you need to draw that in, 1, 2, 3, 4. Perfect. What do we fill that empty space with? 0. So 76,130 is the original value. 6.8 times 10 to the 10th. Which direction? William.
Right.
How many times? Alex. 10. So start at 6.8. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fill in that number, all those empty spaces with zeros. Okay. And what do we got here? 68 billion. Alex.
Oh, do you have to put the commas?
Yes, you should put commas. Yep. You should put commas. 5.1973 times 10 to the negative 7th. Which direction are we going? Left. How far? 7. Okay. .0.0000051973. Okay. 8.21 times 10 to the negative 2nd. Which direction? Kylie? Sorry? Left. How far? 2. So if we start with 8.21, we're going to the left 2, 1, 2. We put a 0 out in front, a 0 to fill in the place, and we have 0.0821. Okay? So that exponent really tells you everything, which direction and how far. Questions on this? Okay. Your homework for tomorrow is going to be to do the second page here. You've got 8 of them where I give you the original value. You are writing it in scientific notation. The next 8, I give it to you in scientific notation. You are writing the original value just like we did on the front side. And then lastly, at the time of this document's last edit, I was about 1.16 times 10 to the 9th seconds old. You need to figure out how many seconds that actually is and then convert to days. How many days old was I at this document's last edit? Yes, sir.
How many seconds are in a day?
Figure it out. You can also just calculate it. How many seconds in a minute?
60.
How many minutes in an hour?
60.
How many hours in a day?
12.
Folks, Alex. Yes, of course. You may use a calculator. Yes, most definitely. Any other questions, comments, concerns, complaints, compliments, congratulations, or criticisms? All right, folks. Homework for tomorrow. Have a great day. Oh, that's how you math.